Welcome to the Kirdridge Observatory. Here we can see the 8-inch f5 Newtonian telescope on the back of the homemade telescope mount. The mount is a standard German equatorial with one motor on the declination axis and a second motor over here on the right ascension axis, which has two pulleys connecting it to the worm wheel. The worm gear moves very slowly, driving the worm wheel, which moves the telescope. Up here is the box containing the Arduino Mega with various other circuits such as the red real-time clock. The Arduino connects via a serial connection to the laptop, which has an ASCOM driver, so familiar software such as Skymap can connect to the telescope mount. Here we see Skymap is now attached to the mount, and you can just see the flashing cursor over Polaris, which is where it thinks the scope is pointing. This window contains all the information about the telescope. We can now right click on a star in Skymap and command the telescope to go to that star. For this particular star, the right ascension axis doesn't have to move far. There it goes. But we can see the declination axis has to move quite some distance, and eventually it stops when the scope has reached the required position. Now if we kick off another go-to, this time we're trying to aim the scope more or less straight up, so both axes kick into action. The Arduino is doing quite a lot of work. When a slew is being done like this, it looks up the current local time from the real-time clock module, converts that into local sidereal time, and then knowing the RA coordinates of where it's trying to get to, it can work out what the hour angle is based on the RA and the local sidereal time. And once it's got that, it converts that into an encoder count and starts slewing the motors until it reaches the required encoder count, obviously slowing them down and stopping in just the right place. We can see in Skymap that our current position is somewhere up here near the zenith. I'm going to ask it to go to a point due south, more or less on the horizon. There's no distance to travel in right ascension, but we can see the declination axis moving the scope down, hopefully until it's almost horizontal. We can see here the drive pulley to the worm gear on the declination axis whizzing around at full speed. And the scope now stops, pointing due south, almost at the horizon. Here we can see in Skymap the cursor flashing where the scope is now pointing. I'm now going to ask the scope to go to a star just the other side of the meridian, so when this go-to starts, the scope will do a complete meridian flip to point at that target. The mount moves at around about 2 degrees a second. That might not look very fast, but it's fast enough, but no faster. Here we can see the right ascension motor running at full speed, turning the worm gear roughly twice a second. When the mount is simply tracking the sky, that worm gear is moving about 1 revolution every 4 minutes. Most of the mechanical components of the mount I've all made myself, mostly using a small mini lathe. This includes the worm gears and worm wheels, which is probably the hardest part to make. The rest of it's just 2 axes connected together with some bearings. As we can see, the scope's making its way around the sky. The Arduino Mega, as I said before, has got a few extra components wired to it, such as a real-time clock and an encoder counting chip. It also uses a small L298 dual H-bridge chip to actually send the power to the motors. Obviously an Arduino can't power the motor on its own. It sends a pulse width modulation signal to the H-bridge driver, which is adjusted to make the mount run at the right speed. The telescope control window contains all the buttons you might expect to find for moving the scope north, south, east and west at different speeds. When we finished using the telescope, we can use the park button to send the telescope back to the polar home position and stop the motors. We can also see data from the accelerometer on the top right there, which is a 3-axis accelerometer telling us roughly where the scope is pointing. That data isn't used for pointing, it's just a guide and a visual check on what's happening. We can now see the scope is going through its park routine. First of all, it moves the right ascension axis to the park position, and then it moves the declination axis. This is to prevent the telescope colliding with the pier during the park, which is a risk if the telescope has tracked a long way into the west. That's pretty much all I've got to show for you today. As we see, the right ascension axis has almost finished moving, and now the deck axis is spinning round to point the scope back at Polaris. There are a few other interesting bits and pieces, such as the periodic error correction, which I will hopefully get to in a later video. You can see the scope's now almost parked, and we should see the park warning light come on. A little white LED down here. There it is, the scope's off now.